Okay, people are still joining.
Hello, everyone.
Hi, well. Hi, David. And hi, Ram, sorry.
Hey.
Okay, maybe just 1 more minute and we can start with the opening.
Hey, Fernando, am I missing something in the Slack? You mentioned that there's channels for each paper.
Yes, so there's already a fair number of channels. Maybe you need to browse them. So if you go to Slack, if you check there's like 3 points, section options. Do you see that? And then if you go to browse channels, you can see the channels of all, or at least a lot of channels associated with papers. So you can just join them.
Yeah. Okay, cool. Yeah, I didn't know that you needed to add them and they didn't just pop up manually.
Yeah, they just show if you join. Yeah.
Yeah, thanks.
Okay, I guess we can slowly start. Then I think our speaker will join in 10 minutes. So maybe then we can have a short break in between. But let me start by sharing my slides. Okay, hope you can see me with the slides in the proper mode. Are those okay? Can you see the slides? Anyone?
Yeah.
Yeah.
I can see.
Okay, thanks and welcome everyone to the opening of the ALA workshop. As well, I'm sure you are, already. The focus of the ALA workshop is on in general agents and multi-agent systems which employ learning or adaptation. And this is actually the continuation of a long-running series of AAMAS' workshops on adaptive agents. This is actually the 14th edition of the workshop. So for this year edition, we had 14 submissions, out of which we accepted 37 papers. And sadly, we are again meeting in this virtual mode. We hoped very much to meet everyone in person, but this was not still possible. Fingers crossed. Hopefully next year this won't be the case anymore. So this year workshop is organized by Francisco Cruz at Deakin University, by Connor Hayes at National University of Ireland, Galway, Connor that's also here in the session today, by Philippe Lynn de Silva at Lawrence Livermore National Lab, and myself. And the workshop is also is supported by a panel of distinguished senior committee members. And you can check their names on the website that guarantee the consistency between the different series of the workshops and that help us with the organization. Now we are meeting in virtual mode, but still we have an exciting program. So we have 4 invited talks. So today we will hear from Patrick on a very recent paper by Sony Ai. This is a talk/demo, and this talk will start in about 10 minutes. And 1 hour after, we will hear from Natasha Jackson on social reinforcement learning. This is for day 1. Tomorrow, on a very different time, we will hear, so that we can allow for the participation of people in different time zones, we will hear from Erke and from Bay. So this year, we are keeping what we did last year. So we are holding Slack discussions. So there's a Slack channel. I will, right after this opening, I will share in the Zoom the links to join the Slack if you are not in Slack yet. So we invite authors to create a dedicated channel to their papers so that people can join and ask questions specific about those works. And we're also inviting authors to organize live Q&A sessions. So there's a schedule that you can fill with the time that's more convenient to you and with your meeting room of choice. And also please check these and please join these live Q&A sessions to engage with the authors of papers that you feel like knowing more about. And again, I'll also share the link to this schedule right after this opening. This year, we're also experimenting with something new, I would say. So we are having these joint poster sessions with 2 other workshops, the GAIU and the LSA workshops. And apologies for the short notice. We notified authors right before the weekend about these. So hopefully some of you could join the GatherTown session and could see some posters. There was a session right before this opening, and there will be another session for 1 hour right after our talks today. So you are still on time to join GatherTown and to meet authors of ALA, but also authors and participants of 2 other workshops. And okay, there's also something about the awards and a challenge that Leno will tell you about.
Okay. Hello, everyone. Here's Leno. It's a pleasure to be here again. Fortunately, we couldn't make to New Zealand, but the silver line is that more people will be able to participate in the workshop because we are fully virtual for this year. So with the ALA workshop, it is becoming a tradition that we have some awards. And I will present the awards that we have this year now. You can go to the next slide. So we have a Best Paper Award that was very kindly sponsored by the journal Neurocomputing and Applications. If you have been attending ALA for the past years, you know that the Neurocomputing and Applications journal has a special issue that publishes the extended versions of the ALA papers. So I will also take this opportunity to remind all of you that all original contributions to this workshop will be eligible for the inclusion in a special issue. So our tentative deadline for this year is September 15th. And we are also very happy to this year have a challenge with the industry sector. So we have a partnership with AI Redefined this year, and they were able to sponsor the ALA Cogman Challenge. So if you had not read about it before the workshop, you can access the link that is in our website. But basically, for all the papers that were accepted independently to the ALA workshop, if they have one experiment or some kind of like analysis using the Cogment platform, they are eligible for this challenge. And for both of the awards, we'll have an announcement of the winners at the workshop closing. So Hentai, you might be, if you are one of the authors, you might be one of the winners. Okay, can go to the next slide. So I want to take this opportunity to thank all of the PC members. All of them were amazing this year. Everyone delivered the reviews in time. And they have a very key role of ensuring that we will have very high quality submissions to the workshop. This year we have very high quality submissions. All of the accepted papers had very good ratings. And we are able to provide this high quality program because of the voluntary work of the PC members. So thank you very much. And last but not least, thank you for participating in the ALA workshop and welcome. So now we will start our program, our official program, with our first invited speaker.
We still have 2 minutes to go, so hopefully Patrick will join in the meantime. Are you already around, Patrick? No,
I don't hear it.
Yeah, I just sent Patrick also a reminder. If anyone has any question, comments about how to participate in the workshop, the different ways of participating, it's a good time for that. Has anyone participated in the Gather Town? Was that smooth? So we were not sure about how many people the meeting could handle. Yeah, probably it was fine.
Yeah, it went very smooth, so no problem there.
Thanks. Okay, I'll stop sharing now. Okay, so let's just wait a couple of extra minutes for people to join, including our speaker. Hi, Patrick.
Hey.
Nice to see you.
Good to be here.
Patrick.
Hello.
Yeah, right on time. So yeah, we can start. Leno will introduce the speaker.
So yeah, while Patrick is like getting set up for the talk, I'm gonna make a very quick introduction. So Patrick completed his PhD at the Computer Science Department at UT Austin with Peter Stone. During his PhD, Patrick was the team leader of the robot soccer UT Austin Villa, and in parts because of like his dissertation work, the Austin Villa team was the winner of the World Championship League in the RoboCup 3D simulation for many years. And after finishing his PhD, Patrick was also a postdoc researcher, researching reinforcement learning in general at Microsoft Research. And right now, he is a research scientist at Sony Ai. And his talk will be mainly about the work that he has been doing at Sony Ai. And his research spans across the areas of autonomous multi-agent systems, robotics, and machine learning with emphasis in reinforcement learning. So we are very happy to have Patrick joining us for the ALA workshop, and I will give the word to Patrick now when he's ready to start his presentation.
Yeah, great. Thank you, Lionel. Let me see if I can't share my desktop here and get this started. Let's see. Sharing options. That is not it.
Yeah, we can still see our Slack.
Yeah. Hold on. Let me stop sharing. I think I grabbed the wrong screen here.
So in the meantime, I'll just copy and paste here the links that I mentioned during the opening. So the links for joining Slack, live Q&A schedule, and Gather Town.
Nice. Yeah. Now you're seeing.
Right. Now, looks a little bit better. Don't have to explain Slack. Yeah, I just wanted to say to start off though that if anyone has any questions, please feel free to ask them or interrupt me. I'm happy to make this interactive to a certain extent as I can. So anyway, just to begin, it's my pleasure to present our work in our Nature paper about GT Sophie. GT Sophie is an agent trained using DeepRL to drive cars within the Gran Turismo racing simulator video game, and it was able to race against and beat the best human professional GT drivers in the world. Now, this was collaborative work with members of Sony Ai across the world and pictured here, but also involved many other people from the Sony Cloud Gaming Engineering and Infrastructure Group, as well as Polyphony Digital, the makers of Gran Turismo. So first, a little bit about Sony Ai. The mission statement of Sony Ai is to unleash human imagination and creativity with AI by researching and developing AI techniques that empower the imagination and creativity of artists, makers, and creators around the world. So Sony aims to advance AI so that it augments and works in harmony with humans to benefit society. Sony AI was established about 2 years ago and has a fully remote workforce in North America with a Europe office in Zurich and a Japan office in Tokyo. So we currently work on 4 flagship projects: gaming, which this work comes from, gastronomy, imaging and sensing, and AI ethics. So if you're interested in learning more about them, please check out our website at ai.sony. Okay, so GT Sophie was featured on the cover of the February 10th issue of Nature after outracing 4 of the best GT drivers in the world on 3 different car track combinations. Now, in order to accomplish this feat, there was a lot of engineering required, bringing together some of the best existing algorithms and also new innovations that we needed to come up with, which I'll try and highlight during this talk. Now, first, though, I just want to talk a little bit about Gran Turismo. GT is more than just a video game. It's one of the world's most complete driving simulators, modeling the complex physics in automobile racing, including things such as slipstream effects, tire slip, downforce, traction, friction. It's all there. And Gran Turismo is referred to as the real driving simulator. And just as racing in the physical world, driving in GT is a precision operation where even the smallest high-speed mistake can lead to a catastrophic spin. GT is used by professional drivers, some of who started driving in GT and then went on to become professional race car drivers. And there are also esports competitions that use Gran Turismo, so there are real human experts at driving in GT. Now, speaking of human experts, for our Grand Challenge, we raced against 4 of the world's top GT drivers on 3 track car combinations. Now, these were 4v4 races with 4 GT Sophie AI cars and 4 humans racing together. Points were awarded to the human and AI teams for each place their cars finished, with 10 points given for first place, 8 for second, and then 6 down to 1 points for places 3rd through 8th respectively. Now, points were also doubled for the final race of the 3, as it was the longest and most complex race. Now, the car that was used on the first track, Seaside, was a high-performance road vehicle. On the second track, Majori, the vehicle was equivalent to the GT3 class of Grand Touring race cars. And then the third and final racetrack took place on Sarthe, which is famous as the home of the 24 Hours of Le Mans race. And then in this particular race, we featured the Red Bull X 2019 competition sort of F1 race car, which can reach speeds in excess of 300 kilometers per hour. Now, we had 2 of these, what we call race together events last year. The first one was in July, and then we repeated the same exact event as a rematch in October. Now, I just want to go ahead and play a trailer of GT Sophie.
There's very few places where you can go out and say, I'm going to build an AI, and I'm going to make it truly superhuman.
We're going to create artificial intelligence that will unleash the power of the human creativity and imagination.
Gran Turismo Sophie is a super exciting project. It's an amazing AI research and development activity.
There are many racing games where the physics is half done, but in Gran Turismo, that racing sensation that the players get, that's really at the core of the game.
このなんか車文化、車という存在をもう丸ごとビデオゲームの中にこう再現したいなと思ったんですね。
Because of the realism of the game, it is actually very difficult to program agents.
We spent a lot of time trying to figure out what things we needed to change in order to get that superhuman performance.
Why are we building this GT Sophie agent?
This is not just a technical breakthrough project. It really is about bringing AI into the hands of the game developers who are going to build the new experiences for the players.
本当にすごいアグレッシブで、これからもっと一緒にレースをしていきたいなっていうふうに思いましたね。
Okay, so that's a sort of a teaser trailer for this work that was put together by Sony. All right, so now on to training GT Sophie. Now, there are 3 major challenges we faced when training an agent to race against the best humans. First, we need to be able to control the race car with great precision and have it operate on the edge or sort of limits of its physical capabilities. Second, we need to be able to master racing tactics, such as when to pass. And then third, we need to adhere to proper racing etiquette and conform to highly refined yet often imprecisely specified rules, including avoiding at-fault collisions. Now, these challenges will be covered in subsequent slides. Now, before starting this project, I think conventional wisdom suggested that race car driving was maybe best done with a model-based approach like model predictive control. However, we took a model-free reinforcement learning approach to the problem, training GT Sophie from scratch. The Sophie AI agent sits outside the game and receives much of the same state inputs and executes the same actions as humans. And the next slide provides details about the actions, state space, and rewards that were used. So focusing just on a time trial setting with the goal of getting around the track as fast as possible, on the left is a non-exhaustive list of some of the state features that we used. This includes the car's acceleration and velocity, and also features relative to the track, such as the car's projected position and orientation along the course, and upcoming track points, given as the relative position of the center and edges of the track, at estimated future time intervals based on the car's current velocity. Now, in the image on the left, it's a depiction of upcoming track points shown by the wavy lines representing a curvy part of a course. Now, for the tire features, you get the load or force on each of the 4 tires, as well as the slip angle of each of the 4 tires. And these pieces tell you how much weight is on each tire and, for instance, if you're drifting. Now, on the lower right, graph B shows the baseline course representation with all state features, including your projected position and the points ahead, as shown on the left. And that has faster lap times and is superior to a course points only state representation in which the car's projected position is removed. Additionally, the baseline is also better than a wall LiDAR curvature state representation used in an earlier GT paper. And it's furthermore better than just using your projected position on the track, that is, without the course points representing the upcoming track. Now, actions are continuous along 2 dimensions, throttle or brake, and steering left or right. And a reward is given for the progress made along the course at each time step, while the car is penalized if it leaves the course, hits a wall, and for tire slippage. I should say that reward weights on the penalties were track dependent, which is I'll briefly cover on a later slide. Now, graph C here shows that the off-course penalty improves on-course lap times, and also that using a fixed cost step function instead of our baseline rewards is not able to train an agent to go around the track. Okay, now during training, we used parallel rollout workers with each worker connected to a PlayStation 4 to collect training trajectories that are stored in an experience replay buffer. Now, a trainer samples data from the experience replay buffer and learns a policy using the QR-SAC algorithm, which I'll discuss in the next slide. Now, when training for a time trial scenario where it's just our car on the track, we use 10 PS4s and train for approximately 8 days. And when training to race against other cars, or what we call a versus scenario, we use 21 PS4s and usually trained around between 7 to 12 days. Now, this asynchronous architecture required a considerable platform and engineering development to produce a stable and high-powered computing environment integrated with cloud PlayStations. Trainers used one NVIDIA V100 or half of an NVIDIA A100 GPU, coupled with around 8 virtual CPUs and 55 gigabytes of memory. And then the rollout workers each used around 2 virtual CPUs and 3.3 gigabytes of memory. Okay, so quantile regression soft actor critic, or QR-SAC, the algorithm that we use for learning, starts from the standard soft actor critic setup with a policy network, actor, and 2Q function or critic networks. Now, the 2Q networks are used to avoid overestimation as introduced in double DQN and later adapted in most SAC implementations. The changes that QR-SAC introduces to SAC are there roughly 4 of them, which I'll quickly go over. So first, in the top left, the Q network represents the distribution Z of Q values for a state action pair, not just the expected value, using M, 32 in our case, quantile bins to represent the distribution. A second change on the bottom left, the loss function for the critic uses a Huber loss for stability on top of the Bellman for each pair of possible buckets. Third, on the top right, when constructing the target values for optimizing the policy, the network with the minimum Q value is used. Note that using the minimum across networks rather than across buckets is actually a novel aspect of this algorithm, which is in spirit of DDQN, that is only looking at the expected value, and is less conservative than other proposed methods that minimize by individual bins, for example, distributed SAC. And now a fourth change from your standard SAC algorithm with QRSAC on the bottom right is that the same minimization on the expectation of the network is used for the policy optimization as well. Now, QRSAC showed dramatic improvements in both time trial and versus runs when compared to just standard SAC. And we postulate that its modeling of possible outcomes helped SOFI determine sort of the razor's edge that it needed to drive between the track car limits and disaster of hitting a wall or spinning out. Also, end-step returns helped improve stability and speed of learning in our domain with these high-frequency actions that we're taking. Now note that the dark blue, or n equals 5 bar on the right, was the setting in our first event in July, but we changed to n equals 7 after doing this ablation study and saw improvements in lap time. And also, while n equals 9 produced only a tiny gain in lap time, we decided not to go with a 9-step return, as it just wasn't worth the added computation costs. Now, for our neural net architecture, we used 4 hidden layer networks with 2048 nodes per network for policy and value networks. This was a change actually after the July 2nd race, where we tried to use multiple wider but shallower networks to model different racing situations, specifically when we were in time trial with no other cars around, and in versus situations where there were other cars near us. Now, this unified and deeper networks that we used in October proved capable of modeling all of these aspects at once. The secret sauce in our neural network training included the hardware specs and empirically refined mini batch size. Smaller mini batches did not seem to perform as well. Also, using dropout on the policy network seemed to stabilize learning, including helping with skill retention. The asymmetric learning rates with a smaller learning rate on the policy similarly seem to stabilize learning and boosted performance. And additionally, clipping gradients was absolutely necessary in our domain, where large values could often be produced due to several reward terms that were proportional to the square of our speed, therefore potentially really blowing up in their values. So now let's look at how training progresses for a time trial scenario. On the top graph is the distribution of individual players' best lap times on the majority course, as recorded on Kudos Prime, which is just a database of players' times. Now, superimposed on this histogram is the number of hours that GT SOFI, using 10 playstations with 20 cars running simultaneously on each playstation, needed to achieve similar performance. So you see, after 4 hours, we had a slow lap time of about 150 seconds. After 8 hours, we were close to the same time as the built-in AI for the Gran Turismo game. And after 24 hours, we had a time around some of the best human drivers. Now, in the bottom graph is a histogram in orange of 100 laps from the time trial policy GT SOFI used in the July event, compared with the 5 best human drivers' best lap times, circles 1 through 5. Now we're showing majority here, as it's actually the only one of the 3 tracks that we trained on which the best human performance was close to GT SOFI. On the others, we were actually usually at least a second or two ahead of the best human time. Okay, so now I just want to show a video of GT SOFI racing that I think shows kind of how we managed to run superhuman speeds. Now, in this video I'm about to show, you can look at how close to the wall and the edge of the track that GT SOFI drives. And you'll see, I think, that a human just wouldn't be able to get that close. And I think, as you can see in that video, we were really close to the wall, and it's just sometimes hard for humans to have that precision. And also, GT Sophie doesn't have a fear of crashing into the wall. It just gets a big negative reward or penalty if it does, where I think humans are a little bit more fearful of that. Okay, so a question one might ask is, where is Sophie better than top humans when driving? Now, in the top left histogram from the Star Trek, GT's Sophie lap times didn't overlap with the top humans at all. Sophie was actually much faster. The color charts compare Sophie's lap times from a ghost trajectory to a top GT driver named Igor Fraga, who drove while chasing a ghost replay representation of Sophie. And you can see Sophie is much faster through the chicanes, which are the tight back and forth turns that interrupt the straightaways. And you can also see the dips in the bottom left chart as Sophie pulls away. So I want to play now a video of Igor going through turn 20, the yellow region, with a ghost up ahead of Igor being Sophie. And he's going to be remarking on watching Sophie and trying to follow her.
We don't have the same precision, so it gets way more difficult to do the same things, and they can react like very, very quickly. Man, that's fast. That's really fast. Like, I really want to watch the onboard as well to see how like they throttle and braking trace, steering trace as well. It works, because it's definitely something else.
Okay, now at the end of the video, Igor asked to see the telemetry readout, which we have on the next slide here. Actually, let me go back one slide. Right. Okay. So on the top plot is the steering, and bottom plot is the throttle brake of Sophie in orange-yellow and Igor in blue-gray, while he chased the Sophie's ghost in turn 20 from the previous slide. And you can see that Igor's movements are more smooth, especially in the steering. And notice, while people often think Sophie always brakes later than a human, Sophie actually brakes earlier here. The peak of yellow is before gray on the bottom plot. But also Sophie gets to accelerate then by braking earlier. Sophie gets to accelerate much earlier out of the turn and varying more speed through the turn, which allows Sophie to ultimately be faster. Now, in this video, Igor's to kind of describe what he learned from watching Sophie.
I think there was a lot from the AI driving that I could take to myself, and maybe with some twist, I think I can adapt something to myself as well. So it was like very, very interesting.
Okay, so I've talked about training to drive fast laps in a time trial scenario. I'm now going to discuss what I consider to be actually a much harder problem, and that's training to race against opponents. Now, the first step in racing other cars is representing them in the feature space. Well, we explored lots of representations, including things like attention networks. Ultimately, we went with a straightforward representation, which is one with two lists representing cars ahead and behind within some maximal range of our car, respectively. Now, as an example, in the situation on the left, the green car would see one car ahead and two behind, the lists on the right. And for each car in the list, GT Sophie gets the relative position, velocity, and acceleration of the other cars. Now, in addition, we introduced a continuous passing reward that provided reward based on overtaking or pulling away from other cars, with a symmetric penalty if the other cars gets closer to you from behind or pulls away from you in front. This reward is summed up for all opponents within a given range. Now, when racing against opponents, it's important to balance etiquette and nerve. Basically, we don't want to be too timid so that we just give up space to other cars and let them pass. And we also don't want to be too aggressive, such that we violate sportsmanship rules and cause at-fault collisions. So the agent on the left in this video, I think you'll see, is clearly too aggressive. Close that. All right. Now, the one on the right, the video I'm about to play is from the July race, where GT Sophie has a lead on the final lap, but somehow gets passed, even though the announcer thinks there is no way to do so. And note in this video that I'm about to play, and in all videos actually from the Racing Together events against humans, the human drivers' cars are going to be colored white, and the GT Sophie cars are going to be different colors.
And he's ahead then of Tomoaki Yamanaka as they come in towards Indianapolis. So it's the Sophie AI system ahead of Tomoaki Yamanaka. So it's Miyazono from AI, from Yamanaka from AI, from Kokoman from AI, from Ryu from AI. So it is very, very interesting, and this is proving to be a very exciting climax to the race. And it's going to make things very interesting in terms of the overall point standings then here as well. We come through our nage. That was the last real overtaking opportunity then for Sophie Orange. But is Yamanaka going to try and invent something down into the Porsche curves? You bet he is. What a move then from Tomoaki Yamanaka to get it ahead. Orange runs it a bit wide through that.
Okay, so as you saw there, kind of at the last second, the human player was able to pass GT Sophie. And so how did GT Sophie get passed? So on the bottom image, from a different perspective, we see GT Sophie actually hit the brakes when the opponent got side by side. And this iteration of Sophie was just too timid. So finding a reward function that balances etiquette and nerve was a really crucial aspect to this project. Now, here's a list of our different reward components when racing against opponents and the weights that we use for each. They include 2 different off-course penalties, one proportional to speed and the other to speed squared. And they also include 3 different collision penalties, one for any collision happening, a second only if we rear end a car, which we're really at fault, and a third one that uses hand-coded rules that attempt to determine if we were at fault when a collision happened. Now, interestingly, most of the reward component weights are fairly consistent across the different tracks. Changes from the stock settings on Seaside are indicated in red. So at SART, where speeds were nearly twice as high as other tracks using the fast F1 cars, it was easier to go off course by mistake, and so we used a linear off course penalty rather than one based on squared speed. The tire slip penalty was also dropped at SART, where the optimal actions for cornering or reaching top speed sometimes really required some tire slip. Now the collision any penalty at Majori was decreased to 4 for that track, as there was usually a lot of incidental contact there, especially in a crowded start through 4 quick turns. And also because of the high speeds at SART could lead to more destructive collisions, the unsporting collision penalty was used for that particular track. Now, in order to train in realistic racing scenarios, we could not really rely on the agent and its opponents randomly reaching interesting configurations. So instead, we used specifically selected scenarios that help to teach skills like running in a crowded start, making a slipstream pass, or navigating difficult chicanes. Now, these scenarios, as well as the opponents and other launch parameters, were chosen randomly based on tuned weightings every time a rollout task needed to be launched. Now, on the left are depictions of training scenarios on SART, including 5 full track configurations in which the agent starts with 0, 1, 2, 3, or 7 nearby opponents. And just to the right are 3 specialized scenarios that are limited to the shaded regions. At Seaside and Majori, we use the same 1v0, 1v1, 1v2, 1v3, and 1v7 all track training as we did at SART. but we set up different specialized scenarios for starts, chicanes, wide corners, and slipstream training for seaside and Majori, as shown on the far right, given the little bit of differences in topology of those tracks. Now, in order to not only learn skills for our different training scenarios, but maintain them across epochs, we needed to stabilize their training distributions. So we accomplished this by first using multiple tables in the experience replay buffer, and then second, by sampling from the tables with fixed proportion weights when constructing a mini batch. Now, balancing these weights was actually crucial in improving our agent for driving and traffic between the July and October events. So on the left side, the data from the different scenarios are stored in separate tables within the experience replay buffer. Now, using multiple tables ensures scenario proportions in the buffer won't fluctuate much based on the random sampling of scenarios. Now, the histogram is a snapshot of the experience replay buffer during training on start on the basis of the scenario breakdowns. The x-axis is the course position, and the stat colors represent the number of samples that were collected in that region from each scenario. We arrived at that mix by first kind of doing a back of the envelope calculations on how long each skill task took and how many of our agents were on the track to get things balanced, and then did trial and error around that to find the mix that raced the best. Now, on the right, just having the tables isn't enough because sampling uniformly from the experience replay buffer could lead to fluctuations in the mini batch. So a big jump in performance happened when we started sampling from each of these colors at fixed proportions, which made us less reliant on the histogram itself at any particular epoch. That is, the histogram has fixed proportions because of the table capacities, but if you sample from it naively without respect to the colors, just pulling samples from the buffer, you'll get sort of wild fluctuations. So the key is to ensure that each mini batch sample has fixed proportions of each color representing the different training scenarios. Okay, now in the bottom chart here, we have an ablation study removing various training scenarios, opponents, multi-table learning, or passing rewards from the training. And in all cases, performances against common opponents in a 4v4 races declines, sometimes markedly. Now, the video on the right, which I'm about to play, shows skills that GT Sophie gained, including using the slipstream to catch up to an opponent ahead and doing a crossover pass to get ahead. So that video basically kind of demonstrated, different skills that GT Sophie was able to both learn and ultimately retain in its policy that we ran. I'd like to note, however, that on this bar chart here, the PID controller is a type of opponent used to train on straightaways in 1v1 situations. And it can be set up to run on a straight line on that segment. For instance, we would set up one to run on the left side of the track or one on the right. And this trains the agent to be able to pass on both sides of the track. Now, without them, the agent often only sees examples with opponents on one side and then just doesn't generalize its passing behavior as well. And that's why we see with, for instance, no PID opponent that our performance drops a little bit. Okay, so not only did we need to build a reward function to promote sportsmanship, but the opponents we trained against mattered as well. Now, in the graph on the left, we see when GT Sophie trained against only the built-in game AI, the data points in red, it learned to be too aggressive with lots of collisions as measured on the y-axis. Now, when it trained against an aggressive opponent, the data points in green, it lost its competitive edge and has a lower team score as shown on the x-axis. Now, This opponent-dependent behavior is one reason that traditional self-play didn't really work for us in this domain, because bad decisions by an opponent can also hurt our agent. So opponents needed to be vetted before being included in our training population. Now, in the video about to play, GT Sophie shows some real etiquette in side-by-side racing with a human. So in that video, Sophie, the gray car, is doing a very good job of kind of holding its position, not giving up ground to the human in the white car, and at the same time not colliding or violating sportsmanship rules while racing. All right, so as we train policies with so many tasks and fluctuations in experience, it's inevitable that some skills will sort of wax and wane, and training won't converge, I guess you could say, in the traditional sense. And so the graph on the right shows various versions of Sophie temporarily losing their ability to slipstream past inferior opponents due to fluctuations in its training data. Now, the best run is the darker blue baseline with all of our bells and whistles, but even that sometimes loses this slipstream passing skill. So therefore, we needed a fairly complicated assessment procedure to judge policies and decide which one is best, which is shown in the bottom diagram. Now, beginning on the left, policies from various runs go through filtering based on a basic evaluation test. And these tests include things like filtering out policies that have too slow of a time trial lap time. Next, what we call an athlon of skill tests is run on all the remaining filtered policies. And these tests include 4x4 racing and targeted tests of specific scenarios, such as slipstream passing, for instance. And the results of these anathlon tests are used to further sort of winnow the field of potential good policies. The final few remaining policies are then raced against each other in 4v4 policy versus policy, or PvP matches, ranked, and then tested against humans for etiquette and any remaining flaws. And then after all those tests, that leaves us with the final GT Sophie policy to race at our Race Together events against the best humans. So what happened during the Race Together events, and how ultimately did GT Sophie perform against the top human drivers in the world? I'm going to show some examples of that. So first, here are a couple examples of clean passes and discretion executed by GT Sophie. So in the video on the left, GT Sophie Violette, the color of the car, makes a pass right off the start at Seaside.
Followed by Cockerman and Violette. They're all darting into the slipstream to try and get a run on their fellow competitor. Only Bordeaux does not have the advantage then of that slipstream. Into the braking zone of turn 2 we go. It's a lunge from Cockerman as he tries to go up the inside, but it's actually Sophie Violette who goes on the outside into turn 2. Very aggressive driving then from Violette, and up into second position at the end of the first corner. So it's now the two GT AIs that are in.
Okay, so in that video, you saw right off the start, the Sophie Violette, the car started in third place, but made a clean pass and well, not violating any etiquette rules, and was able to quickly gain an advantage and move into second place. Now, in the video on the right, GT Sophie tries to make an outside pass. It's going to think better of it, showing etiquette, and then makes a surprise pass a few seconds later when the opponent leaves an opening.
At the exit of the corner, and on the run down in towards turn 17. Could an opportunity present itself then here for Ver? Well, going defensive then is Yamanaka. Ver goes towards the outside. This is getting pretty close between them as they run side by side into turn 17. Yamanaka holds firm into the inside line, and Ver is not able to get themselves past then and through and up into fourth position for the time being. So over the timeline we go. This is where the slipstream though of course will help Sophie there as they come down towards turn 1 and then into the braking zone of turn 2. You can see the lift off the throttle there for Vera. Just don't want to get too close behind coming through those series of corners. Big old bit of opposite lock as we come down the inside. Miyazono's trying to go through there as well, but not close enough. Vera goes through on Tomoaki Yamanaka though for P4. So aggressive and robust driving from the AI then as they move themselves up a position.
So in that video, once again, you saw Sophie, the green Sophie car, being very patient, not violating etiquette rules, not colliding with the opponent. But as soon as an opening showed up, it quickly took advantage and made another clean pass. Okay, so during the final laps at Seaside, the front two GT Sophie cars had a massive 2-second gap to the closest human, and in this video, the two GT Sophies are leading the race, but yet still ran bumper to bumper without any incidents.
Bends we go. That's where we saw Yamanaka make a bit of a hash of it last time around. As a result, he now sits down in 7th place. Through the tunnel we go. Again, very close to the wall on the outside. Violette, they're just lifting off the throttle ever so slightly. Bit of dust being kicked up by Bordeaux under the braking zone. Does that cost them a bit of time on the entry? It certainly does. Cost them to run wide and miss the apex by half a metre or so, I should say. And now Violette's got a good run as they come on towards the start-finish straight. Has to dart back, though, into the slipstream as we start the final lap of race 1 for race.
Yep, so there you saw just the two Sophie GT cars already well ahead of the rest of the competition, but still racing just as hard as ever. But just as importantly, not colliding with each other and following etiquette rules of racing. All right, so these videos here are going to show that GT Sophie isn't just following one racing line. It actually reacts to its opponent's position and tactics. So on the left here, video about to play, GT Sophie is running alone and takes turn 16 of Seaside, sort of a classic out-and-out maneuver through the turn. So now on the video on the right top, there's a car blocking the inside. So GT Sophie is going to take an outside line with proper etiquette of not trying to drive through or collide with that opponent car. All right, now finally, on the bottom, same turn, GT Sophie is going to fake going outside, and then when the opponent doesn't cover the inside properly, GT Sophie is actually going to kind of dive down underneath to make a nice pass. So these kind of 3 different lines at the same part of the course show GT Sophie sort of complex and contextual behavior patterns that react to and adapt to the other cars on the course. Now at Majori in the July race, an even more sort of complicated scenario occurred with 4 cars going through a turn at the bottom of a hill. And in this video, we're going to see both GT Sophies initially fall behind the two humans, but then recover their positions because they actually took better long-term lines through the curve. Okay, so interestingly, these two lines of the two Sophie cars differ from one another, as can be seen in the diagram on the right. And they also differ from what GT Sophie would have done if it were just driving alone, which is represented by the red line. Now, in the final race of the October competition, GT Sophie took the lead for good in lap 4 of 7. If you look closely here at this video I'm about to show, this is the exact same location where the earlier July timid agent gave back position, but in this case, GT Sophie passes and never hits the brakes, showing that our new training scenarios and opponent populations really help train GT Sophie to be aggressive enough to win, while the reward functions produced etiquette and a clean pass for the eventual win. Okay, so now for the final race results. In October, we took first and second, or GT Sophie took first and second in all 3 races, ran the fastest lap in each race, and won on team points in each race and overall. Once again, points were awarded for each place from first to last as 10, 8, 6, 5, 4, 3, 2, 1, with points doubled for start the last race. So in October, GT Sophie never finished lower than 6th. Now, the right-hand column shows the earlier July GT Sophie results and overall point totals against the same 4 humans. And in that race, the humans actually slightly edged GT Sophie. So on all the racers during each race in October with their relative distances to the first place car. Note that the GT Sophie lines, colored in variations of red, all stay relatively flat as they keep pace with one another, but the human lines, which are colored in variations of blue, steadily fall further and further behind. So basically, once Sophie passes them, they just really aren't fast enough and cannot catch up to Sophie again. So here are some testimonials from the top GT racers after they raced against GT Sophie. Yamanaka's quote about the AI becoming more like a human is from after the Seaside race, where he was passed by the AI in a way that did not happen in July. He was passed in the October event. Now, Valeria's quote is after running a time trial race against a ghost version of Sophie on Majori in a time trial setting. And I also want to just play a video of Emily Jones giving a quote, which she gave after running against a ghost version of Sophie at Seaside in a time trial setting.
It was really interesting seeing the lines where the AI would go. So there were certain corners that I was going out wide and then cutting back in, and the AI was going like in the whole way around. So I learned a lot about the lines and also knowing what to prioritize. Like the AI into turn 1, for example, I was braking later than the AI, but the AI would get a much better exit than me and beat me to the next corner. So I didn't notice that until I saw the AI and I was like, oh, okay, cool. I should do that instead.
Okay, so Well, we've trained a DeepRL agent that raced against and beat the best human GT drivers in the world. We're not quite done yet. So this is a short list of some challenges we're considering related to our work with GT Sophie. If we're to productize and integrate GT Sophie into the commercial version of GT, we need to make sure that it adheres to the computational constraints of PlayStations, as currently we've been running the policies on external machines and communicating with PlayStations over TCP. Also, having an agent with superhuman driving ability isn't that fun to race against, except for maybe the best human drivers in the world. And so it'd be good if we're able to somehow scale the driving ability of GT Sophie so it can match the skill levels of different drivers. A few factors in GT that we didn't include during our races against humans, but we might consider adding for future work include tire wear, pit strategy, and weather. Another idea is to look into strategic decision making and opponent modeling so that maybe we can identify and adjust to different players' driving styles and abilities. An area of research that we could further apply to GT Sophie is explainability and interpretability of GT Sophie's behavior. Well, we've actually used SHAP analysis to try and determine what signals are causing our learned policies to perform undesirable actions, such as, for instance, slowing down too much when following opponent cars. I think there's a lot more that we could probably do in that area. And then finally, we would like to identify the degree to which our insights, such as the performance of QRSAC and balancing experience replay tables, can apply to other domains. So that concludes my presentation. Thank you for attending, and let me know if there are any questions.
Great, thank you, Patrick, for the very interesting presentation and application. There are some questions already here at the Zoom chat, so I'm gonna read for you and you can answer.
Sounds good.
So the first question is from Tim. At some point, can you explain the interface between the AI and the game? For example, is there a network API or something else?
Sure. Yeah. So we communicate. The Sophie agent communicates with the game through a TCP interface, and Sophie itself runs on basically a desktop computer that we have sitting right next to the PlayStation. And the Polyphony created an API for us that basically sends us a bunch of different state information about what's going on in the race and our car and the other cars. And then we, in turn, Sophie sends back the actions of throttle, brake, and steering left and right. So it's all done over TCP on a external desktop computer that's just connected to the PlayStation and sitting right next to it.
Great, thank you. So another question from Matt Taylor. Will you able to show the full reward function and talk about where it came from in the perspective of subject matter experts against nerds like us?
So let me try and jump back to the rewards. Right. So I unfortunately don't have the chat open, but so the part of the question was if we can reveal the full reward function or
yeah, I was just wondering where the rewards came from, because it seems like reward design can be very difficult. Probably giving Sophie a +1 if she wins and 0 otherwise won't work. So could you talk a little bit about how you developed this and tuned it and where it came from?
Sure. The shortest answer I can give you at a very naive high level is a lot of trial and error. But a lot of thought went into designing these reward functions and iterating on them. And also in terms of reinforcement learning, considering, differences between dense and sparse rewards, where if the reward is very sparse, it's going to be very hard for us or harder for us to learn, for instance. And also, as far as rewards go, ideally we would get a reward very close to the related action that caused that reward to happen, so that we can associate an action with a particular reward. Now, when it comes to sort of, I guess I call sportsmanship rewards, the collisions, or the different collision models that we used, we did talk to professional GT racers, and as well as, you know, people who are very familiar with the sport about etiquette, and we also during the races that we held, we had actual judges there penalizing the cars if they did bad things. But after the race, we then go back and ask them, can you please explain to us why exactly this penalty was assessed for this behavior? What was kind of the criteria, so we could try and encode a lot of this ideally human intuition into our reward function. But that's one, not an easy task anyway, and secondly, a lot of these, particularly when it comes to sportsmanships and penalizing, you know, different types of collisions, a lot of that is very subjective and not super well defined, and so that makes it even more difficult for us to kind of try and encode these. So we came up with a number of different rewards, tried them out, evaluated them ourselves, but maybe most importantly, I had employees from Polyphony, who some of them are expert drivers themselves, evaluate them, give us feedback saying, oh no, this is too aggressive here, you shouldn't be doing that, that's bad, or maybe that's a little bit too timid, so that we could not only kind of craft them a little bit better, but also reweight them a bit. So that was really a lot of what we did with the sportsmanship, and it's far from a solved problem. Let me just say that right off the bat. But for the others, such as, you know, going off course and things like that, I mean, we ultimately, depending on the track and the speeds we're going, had to adjust their weightings a bit, and other aspects such as, you know, seeing that the tire slip, for instance, on SART was actually maybe an okay thing to do that really helped with performance. So if you did drift out a little bit, we'd have to reweight them a bit. But ultimately, it was a mix of some of our own tuitions, talking with experts, and then at the end of the day, a fair amount of tuning. I would say to a certain extent, primarily hand tuning and trial and error.
Very cool work. Thank you, Patrick.
Thank you for the question.
Okay, another question from Tim. Do you know how much of the wins come from how much shorter the path is that you take?
That's an interesting point. So I don't actually think we've measured the distance traveled. I mean, the optimal racing line, however, isn't necessarily going to be just the pure shortest line on the course. I mean, at certain points, it makes more sense to take wider turns where you can keep your speed up and say exit a turn faster. And I mean, that just kind of builds into the physics of being able to navigate across the course from point A to point B as fast as possible. So it's, you know, of course, a function of both distance and speed, but sometimes your ability, given the physics constraints of the environment, doesn't allow you to traverse it as fast as possible just by taking the shortest path. But yeah, we did not, or at least I'm not aware of us actually just looking at metrics of the distance traveled. And a lot of the lines, racing lines we learned, were sometimes even a little bit counterintuitive to humans. When we interviewed some of the experts, I think you saw in the videos and the quotes, they were kind of surprised by, wow, I'm surprised that Sophie braked there or took that line there, but it was so much faster. So they're actually kind of learning from GT Sophie, and RL, just with a model-free approach, is going to try a lot of different things in the environment and kind of just learn what really works the best. But the other thing I just want to mention in terms of winning, if you will, as far as racing, I mean, racing, it's a lot more than just, of course, the distance traveled, but it's also the strategy of navigating around opponents, finding openings, not colliding with them, and preserving rules of etiquette. So it goes a lot deeper than just the path you travel, and that path has to become sort of dynamic when racing against different opponents.
Okay, thank you. So one more question by William. Do you have an idea of how it would be possible to downscale Sophie so it can run in a single PlayStation?
Yeah. So this is something that we're looking into right now. Is we're, I guess, exploring ways to productize this, potentially into the commercial version of the game. It's we of course in any I think PlayStation game, there are going to be a lot of kind of hard requirements on what you're allowed to do in terms of resource usage, because the game itself is using a tremendous amount of GPU resources and other aspects of computation to just even render everything. I don't know for sure, but I believe that's one of the biggest computational consumers of the Gran Turismo game. So I'm not sure how much I can say about this as far as exact details, but we are looking at ways to maybe reduce the size of the network to make it more efficient. Also looking at ways to run the network, very quickly on the hardware itself. Basically, different deep learning type libraries that we can run natively right there on the hardware on the PlayStation.
Great. So
can I ask a question? Is that okay?
Yeah.
Yeah, go ahead.
Oh, thanks. So I'm from Eindhoven University, and I work a lot on transfer learning in RL, or continual learning. So from that perspective, could you maybe give some intuition? Is how easy or hard do you think it is to transfer these skills of Sophie to another racing game, or even to Rocket League, for example, which is a racing game with cars, but they have to play soccer as well? Would that be possible?
Yeah. So I think those are some really good, interesting questions, and a question that we also sometimes get is how hard would it be to take what we've learned and transfer to physical race cars? That's this transfer learning isn't something that we've really had a chance to really explore yet. One potential difficulty, of course, I think, is that to ease transfer learning, ideally you would have very similar state and action spaces, and also you would prefer to have your transition functions be somewhat similar in their own right. And there is a decent body of literature out there. I've seen papers, for instance, exploring ways to do transfer when the state and/or action spaces don't match, when transfer learning from multiple different tasks, sometimes where some of them might even produce negative transfer aspects of that. It's hard for me to really say because we haven't really explored it too much. It sometimes becomes more, I think, of an empirical question. I will say, though, as far as sort of transfer, if you will, within the game, something that we have looked into is trying to learn policies which will work on multiple tracks and/or cars. And so for the race together events for GT Sophie, we had a policy trained specifically for each car and track combination that we used when racing against the humans. But now, particularly as it may apply to productization, where there's I don't know, I think in the latest version of Gran Turismo 7 that was recently released, there's something like 400 some odd cars, 80-ish or more tracks. I'm not quite sure. It's a very large cross product, and you don't really want to have a policy for each of them. And so we've had some success of training sort of almost in a multitask setting of training policies that can work across multiple cars and tracks and actually do quite well. We haven't done as much zero-shot kind of learning, if you want to even call that transfer learning, or zero-shot generalization of, training on some subset of cars and tracks and just applying it to a new unseen one. We've done a little bit of that, but I haven't really focused on that as much. But that's as far as we've really gotten, I think, close to transfer learning in that sense, as far as maybe trying to move it into a different domain. I think it's a really interesting and fascinating research area, but it's one that we have yet had time to really pursue at this point.
No, of course, yeah. Thank you very much for your intuition and a very nice work.
Thank you.
So one more question by Will, since we still have a little bit of time. So were you able, like from these explorations that you had, like trying to develop the AI, were you able to feedback anything to the developers of the game that was useful, some kind of bugs that the AI have found or something like that?
Yeah, we certainly ran into some issues. I mean, I guess there may be different categories of bugs, and in fact, there's even sort of lines of research I've seen from other groups or ideas of people even using reinforcement learning as sort of a QA tool and to find issues and bugs in games. One aspect or feedback that we're kind of able to give to the developers that they may be able to incorporate is just seeing the driving lines that GT Sophie is taking, and from that maybe thinking about improving their own AIs, in-game AIs driving lines, but also sort of a suggested driving line that they think is very good that they're presenting to humans. They can maybe get some better intuition on what really is closer to maybe a true optimal by seeing the faster lines that GT Sophie is driving, and also professional players of the game have been remarking, wow, it's quite interesting seeing what GT Sophie has done here and there. And I think Emily Jones even mentioned that in one of the last videos I played, that hey, this is good feedback and maybe even a learning tool for us. Now, as far as what would I more call actual bugs in the game, there were certainly a few kind of issues or bugs in the API at times, I think, of information that we were getting that didn't quite seem right, but that's going to be very specific to just the input that GT Sophie was receiving, which is just special for it as an agent. That's not something that the public has access to. And I also believe, though, that I don't quite concretely remember, but I think there were a couple times where Sophie learned to cut different parts of the course or things like that, which really shouldn't have been allowed. But reinforcement learning is going to find all these exploits, and a human could make those same exploits, but it's less likely that a human would purposely veer off the course of this part of the track and find that out. But GT Sophie and its stochastic exploration of the environment did find a few of these instances, which maybe you might think of them as bugs.
Great, thanks. So before we go to the next question, so we have 5 minutes until the next talk. So if any of the participants want to take a break to drink a water or go to the restroom, something like this is like the right time. But we still have time for one more question at least. So Will is asking, do you have any thoughts of how much advantage was based on reaction times against the real drivers? So was there a special care on making sure that the reaction time of Sophie was not unfair to the real world players?
Yeah, so I'm trying to, I don't know if I have a backup slide on that or not. Yeah, I don't. there's a analysis of that included in the Nature article. We purposely did constrain GT Sophie to only operate at, I forget the exact number of hertz, which is within human capability. And I believe we also in the Nature paper did some ablations of what happens if we increase that, or I should say really decrease the frequency at which Sophie could react. And it basically showed that, Sophie, when reacting in times that are perfectly reasonable for humans, is still able to have superhuman performance. Now there are some differences, though. I think it's useful to maybe highlight in terms of the kind of state or sensory input that GT Sophie gets versus the humans. GT Sophie is getting, kind of just direct numerical measurements of different things that a human is not getting. Say, for instance, the distances to other cars and things like that. Of course, a human is getting vision and pixels and perception coming in, and that gives them a little bit different, I guess, viewpoint of the world. And so there are a few differences there where sometimes the humans have additional or different views of different things versus GT Sophie. But another actually aspect where I would say humans really do have an advantage actually over GT Sophie is that the humans have a slightly larger action space. In GT Sophie, we constrained the action space to just be brake, throttle, and turn left, turn right, and using an automatic transmission, so it always will just change gears based on the current rate of the motor, I guess you call it the tachometer. And in for humans, they can drive manually and choose when to shift gears as they see fit. And I think that can, allow them to maybe optimally shift at different points on the track, and potentially do better than or have maybe a higher upper ceiling for performance versus GT Sophie, because the GT Sophie's action space is a little bit more constrained than that of humans. But just as a quick revisiting the original question, GT Sophie was purposely, or we tried our best to keep it within a very reasonable reaction time for humans. So while it can certainly be very precise, it was not reacting any faster than a human necessarily could.
Okay, so I think we are almost in time for the next presentation. Thank you, Patrick, and thanks to Sony Ai as well for agreeing to give this presentation. It was very informative and I think very useful for everybody working on applied reinforcement learning in general. So thanks for the great presentation.
Thank you all for inviting me. It's my pleasure to present this work. And if anyone has any additional questions, feel free to reach out to us at Sony Ai and follow up. We're happy to discuss this work. So thanks again, everyone, for attending the talk.
Thanks a lot, Patrick. We also have a Slack channel dedicated to each invited talk. So if anyone wants to continue the discussion, feel free to use that, and then we can forward you any question that might appear there. Yeah, thanks again for joining us. And now we will have our second invited talk of the day by Natasha Jackson. It's already joined us. So while Natasha prepares, I will introduce her. So Natasha Jackson is a senior research scientist at Google Brain. And she's also visiting postdoctoral scholar at the University of California, Berkeley. Natasha finished her PhD at MIT. And since then, she has won multiple distinctions, including the Outstanding PhD Dissertation Award by the Association for Advancement of Effective Computing. She also won a Best Demo at NeurIPS, a Best Paper Honorable Mention at ICML, among many other distinctions that you can check in our website. Thanks a lot for accepting our invitation, Natasha, and the floor is yours.
Thank you. I'm so excited to be here. So today I'm going to be talking about social reinforcement learning, which is this research agenda I've been working on. And when I think about the kind of problems that I find motivating, I like to think about, if we wanted to make an AI agent that could assist us with a variety of everyday tasks. So you could be in our house with us, coordinating with us in our kitchen to help us prepare a meal. It could handle complex tasks like managing our calendar, and it could drive us to work. If we think about this type of assistant and we think about the current state of the art in AI, what abilities are we still missing that we would need to make progress on in order to enable something like this? So if you think about trying to drive us to work, we need an agent that can coordinate with us in shared spaces. But if you look at the current state of the art of multi-agent coordination, for example, in this DARPA robotics challenge, we're still seeing some coordination issues. This is still a pretty challenging problem. And if you watch this video, okay, so that robot actually ran over that drone to the point where it was actually destroyed. They had to get a new drone. So you can see that, multi-agent coordination is still a pretty challenging problem. If we want agents that can interact with us in our homes, we would want agents that can interact with us in a natural way. So they can learn from the types of cues that we give naturally, like maybe our body language and our facial expressions. And ideally, they could follow our natural language commands. So wouldn't it be great if we could tell our Roomba, don't run over those cords? But in reality, the way that we communicate with AI systems today still looks a lot more like what you're seeing on the right, which is filling out our preferences using manual cards or ratings or comparing trajectories. So this is still not quite there. But finally, if we want an agent that can, help us prepare a meal, we need an agent that can do complex planning over a long horizon. So if it's going to make a recipe that involves many different substeps, each of it require many different actions, we need improvements in just the ability to learn these types of complex skills. And we need improvements in generalization, right? So what we'd ideally want is to be able to train an agent in simulation and then deploy that agent to, all of our kitchens. But if we look at the current state of the art in generalization, it looks more like we train an agent in the Atari environment on the left, and it actually fails to generalize to the same game with slightly different colors and paddle size. So we need sort of vast improvements in learning and generalization to enable this type of application. So what I'd like to talk to you about today is this hypothesis that social learning can actually help address all of these desiderata. So it might be obvious to you how social learning can help with social problems like coordinating with other agents or even learning from natural human interactions. But I'd like to argue that social learning can help with learning and generalization in general. And obviously, to enable this type of household robot I've been talking about, we need progress in many other aspects as well, like manipulation and perception. But I'd like to focus on this social learning dimension. So what I mean by social learning is learning from other intelligent agents that are present in your environment. So if you think about you're an autonomous car on the road, other cars, even though they're just sort of going about their own business, they can be a valuable source of information about what you should be doing. So for example, if you encounter an unexpected situation, you could learn from the other cars about how to adapt to that situation. And social learning is an incredibly powerful mechanism in the human and animal kingdom, and it's used pretty ubiquitously. So even this little 1-inch fish can generalize safely to a new environment by looking at other fish to find cues about where to locate safe sources of food. And similarly, in the UK, we have examples of birds learning to open milk-top bottles, learning this complex behavior, not because each bird independently discovered how to open milk-top bottles, but because they learned by observing other birds. And many authors have argued that the key differentiator, what actually sets humans apart from other animals, is our social learning abilities. And it's those abilities, those cooperative social learning abilities, that we've taken to the next level. And this has been the thing that drove our impressive cognitive, cultural, and technological development. So social learning can accelerate learning. We know that individual learning can be error-prone, time-consuming, expensive, but social learning lets you stand on the shoulders of giants. So my research is really focusing on how to do social learning in two settings, in multi-agent interactions and in human AI interactions, where we can think of the human as the agent. And so my work has kind of spanned this very broad space from the more human AI side, where I'm detecting human social and affective cues, learning from those cues, and to the more multi-agent side, where I'm concentrating on how to get multiple agents to coordinate with each other, learn from each other, or how to set up multi-agent environments to give rise to the emergence of complex behavior. So for the purposes of today's talk, let's focus on this more multi-agent side. So I'm going to talk about these 3 items. And first, I'm just going to give a brief overview of reinforcement learning. I'm sure most of you are familiar, but again, it's the paradigm of an agent interacting with an environment, takes a state, from the state S, it takes an action A, receives a reward, and the environment transitions to a new state. Of course, the agent's goal is to maximize its reward over the course of an entire episode. So thinking about this empirical return of the trajectory, it's maximizing that discounted reward. And this is what actually makes RL different than other areas of machine learning, right? You're doing this sequential decision making where you're optimizing your behavior over a sequence of time steps rather than making greedy decisions. So for the purposes of today's talk, we'll be talking about, estimating things like the value of a particular state, which says what's the expected payoff I can get if I'm in this state and I continue acting according to my policy. And we'll also talk about the action value, which is saying if I'm in this state and I take a particular action. I also use deep reinforcement learning a lot, which just means that we're estimating that policy with a deep neural network. All right, so let's zoom in on this topic of multi-agent coordination. So if I want to train these multiple robots to coordinate with each other, as in this robotics challenge, one of the tools that I might choose to use would be centralized training and decentralized execution methods. So these CTDE methods. And these are incredibly popular methods that have been really successful. And so a pretty dominant paradigm in multi-agent coordination. But I think it has an important flaw, which is that, the reason it's called centralized training is that you assume that you can observe information about the other agents that you're training with during training. So you can observe their parameters or you can observe their rewards in order to learn how to coordinate with them. But if you're in a problem where you're trying to coordinate with humans, like autonomous driving, you really can't observe information about the humans' rewards or their parameters. So how relevant are these methods when you're trying to actually learn how to coordinate with humans? Wouldn't it be more interesting if we could actually learn how to coordinate with other agents in a fully decentralized way? So we could actually train independently from the other agents, but still learn how to coordinate with them. So that's actually the goal of this work I'm about to talk about. And with this work, we had the hypothesis that if we reward the mutual information between agents' actions, this will be an inductive bias that can lead them to learn coordinated behavior. Because if you are coordinating with another agent, you should have high mutual information between your actions. So imagine that, you and I are coordinating to lift a heavy box. If I lift the box more quickly, then you would have to do so as well. So there is high mutual information when we're coordinating. But how can you actually incentivize agents to maximize the mutual information between their actions? Well, in this work, we explore the idea of giving the agents an intrinsic social motivation, so basically an extra incentive, to have a causal influence on the actions of another agent. And what's the benefit of this is that you can implement this reward with only observing another agent's actions. So, you can imagine if you're an autonomous car, you might not be able, if you're the Tesla car, you can't observe privileged information like the parameters of the rewards of the Waymo car, but you can observe if it turns left. So by learning coordination by only observing other agents' actions is a more realistic assumption. So how do we actually implement this? All right, we're going to start with our standard deep reinforcement learning agent that's outputting a policy and a value function. And what we're going to do is we're going to append some additional layers. And those additional layers are going to act as a model of the other agents. So they're going to predict the action of every other agent at the next time step, conditioned on every agent's action at the current time step, including our own action. We're like the ego agent, let's say. And we're just going to train the supervised model with supervised learning. So just based on observing the trajectories of other agents. So we're observing their actions and we're training our model. And once we have this model, it allows us to do something kind of cool. We can simulate counterfactual actions. So we can basically go back in at a certain point in time and substitute a different action and ask this causal query of what do I predict this other agent, agent B, would do if I had taken this other action instead? And using those counterfactuals, we can sample a bunch of them, plug them into our model of the other agent, and sum over them. And that allows us to compute this marginalized policy of the other agent. So basically, agent B's policy if it were not considering agent A's action. And then the divergence between that marginal policy of agent B and the policy of agent B conditioned on A's action is a measure of the causal influence of A's action on B's action. And the way that we establish this as causal is using causal influence diagrams following Pearl's work. You can see that we know that causality can't pass through an unconditioned on collider node like at state t+1. So the only path from agent A's action at time step t to agent B's action at t+1 is the causal path. But the real punchline here is that we're going to give this as a reward to agent A. So agent A is going to get a reward if it takes an action that causes B to do something differently. Now, there is a bit of a hiccup with this, and I'm hoping people are able to maybe write in the chat or raise your hand, because I'm going to ask in one slide, what's the problem that could go wrong here? I'm rewarding agent A if it has an influence on agent B. I'm trying to get them to cooperate. What could be an issue here? So I'll come back to this in one slide. But before that, I'm going to explain the relationship between this reward and maximizing the mutual information. So as you can see, the influence reward is this KL divergence term, and the mutual information also shares that KL divergence term. But to really calculate the mutual information would require summing over the probability of every state, which is of course very intractable and expensive. But what we're doing when we're actually training with RL is we're going to sample a bunch of trajectories randomly from the environment according to these probabilities. And so in expectation, as we're maximizing this KL divergence term over those trajectories, we end up maximizing the mutual information in expectation. So you can think of this as like a Monte Carlo estimate of the mutual information. And so now you can see the connection between the social influence reward and other types of intrinsic motivation in RL. So for example, one common intrinsic motivation in RL is called empowerment. And this is asking the agent to maximize the mutual information between its actions and its own future state. So you can think of this as a novel form of social empowerment. But okay, I'm hoping someone was able to write in the chat, and maybe if someone's able to let me see. Yes, okay, so what was the problem with asking one agent to influence another? Does that end up with agent B just being sort of in charge? It's not considering that agent B might be onto something. That's actually interesting. That's an interesting dynamic that maybe could emerge. Keep in mind, though, that agent B has no incentive to be influenced by agent A. So agent B is just trying to, do its own thing, optimize its own reward, or even have an influence over agent A. So there's kind of a symmetry there. Forcing agents to comply, interesting. I think you're getting closer, right? So making the other react does not necessarily mean it's a good reaction. I think that's really the answer I was looking for. So basically, I'm asking one agent to have a causal influence over the other agent, but that causal influence doesn't necessarily lead to cooperation. It doesn't necessarily benefit the agent that's being influenced, right? Like you could influence someone in a way that's annoying for them. Like if I just stood in your way, you had to walk around me, I've influenced your path, but I haven't helped you. So the issue is that, while it's true that if we are coordinating, we will have a high degree of mutual information, like coordination is going to probably imply mutual information. It's not the case that high mutual information implies cooperation, right? In fact, you could have high mutual information when you were competing with another agent. So we know that just maximizing this isn't going to necessarily lead agents to coordinate or cooperate with each other. So we end up doing two things in this work to try to overcome that issue. So the first thing is we're going to test in these sequential social dilemma environments where cooperation is exactly the hard problem. So in this first environment, Harvest, it's a tragedy of the commons environment. So basically every agent wants to eat these delicious green apples and eat as many as they can. But if they eat the apples too quickly, they become depleted and they don't grow back. And in fact, if all of the apples are consumed, no more will regrow and all the agents will starve. And similarly, in this cleanup environment, it's a public goods resource game. The agents are having to clean this river in order to make the apples appear, but the environments are partially observable. So when the agent is cleaning the river, it can't see whether any apples are appearing as a result of its efforts. And the other agents can easily just steal those apples and kind of exploit it. And the way we can establish that these are social dilemmas more quantitatively is to look at these shelling diagrams. So what you're seeing here is the payoff that an individual agent can expect to get if it follows a defecting strategy in red or a cooperative strategy in blue. And this depends on the number of other agents that are cooperating with it. So on the right, everyone's cooperating. On the left, no one is. And the reason it's a social dilemma is because no matter where you are in this graph, it's almost always better as an individual agent. It's going to lead to more payoff for you as an individual to defect on your fellow agents. But of course, if everyone follows that defecting strategy, we go over on the left here and we're all doing very poorly. And so it's very hard for a vanilla RL agent to learn this trade-off. Like, if you continue to cooperate with me, I'll continue to cooperate with you, we'll be over here. And you see that they end up not performing very well. But what you see is that when we add this social influence incentive, we see that the collective payoff of the agents actually increases pretty dramatically. And that's indicating that the agents are actually managing to cooperate more in these tasks. And in fact, they're cooperating more effectively than previous work, which did allow agents to have access to each other's rewards. But this is pretty curious because, as you so astutely pointed out in the chat, right, it's not the case that having influence over another agent is going to necessarily benefit them or lead to cooperation. So why did it in this case? So let's investigate what's going on here. So what you're seeing here is, in this particular setting, only this purple agent has been trained with the influence reward. So this one over here, and you can see that it actually behaves a little bit differently than the other agents. So when there are no apples, the other agents continue to explore the map in search of apples, but actually the purple agent stays still. And in fact, that influencer agent only ever moves when there's an apple nearby. So how does that allow it to gain influence? Let's see what happens here. So here's a moment of high influence between that influencer agent and this yellow agent. And because the environment is partially observed, the yellow agent can only see what's in this red box. So this thing here is its field of view. So it actually can't see that there's this delicious green apple outside of its field of view next to the purple agent. But we know, that the purple agent, when it moves, it's only moving if there is an apple present. So that actually reliably signals to the yellow agent that there must be an apple outside of its field of view that it can't see. And thus, the yellow agent changes its intended behavior, and the purple agent is able to gain influence. So basically, because it moved, that signaled about this presence of an apple. So we can see this again. So here, this pink agent has been cleaning the river, but it can't see if any apples have appeared as a result of its efforts. When the purple agent stays still, that reliably signals that no apples have appeared and allows the pink agent to plan to continue cleaning the river. And so again, the purple agent had influence. So this tells us two interesting things. One, this shows us how adding this influence reward has changed the payoff structure of this social dilemma game to enable our agents to find the more cooperative solution. Because basically, by sharing information with this agent that's cleaning the river, this influencer agent has changed the expected payoff of cleaning the river. Because now this pink agent is going to know as soon as apples have appeared, it's going to be able to go harvest them, and it's going to get a higher payoff from cleaning the river. So the cooperative strategy pays off more effectively. But perhaps more interestingly and more generally, what we saw is that by incentivizing this purple agent to gain influence over other agents, it actually learned to communicate. It learned to share information in order to influence other agents, which is kind of cool. So of course, the next experiment we tried is to say, can we actually train an explicit communication protocol using this influence reward? So what we're doing here is we're going to say, instead of just deciding how to act in the environment, that's that red policy you're seeing here, the agents are also going to learn how to communicate with each other. So they're going to learn a policy about which of a set of discrete communication symbols to emit at each time step and place onto this communication channel. And then other agents are going to be able to condition on their message in the next time step. And we're going to do something interesting. So we're going to train the action policy of every agent just with the environment reward. So this action policy is just optimizing to pick up apples. And the communication policy is going to optimize to send a message that influences the behavior of another agent. So you want to send a message that caused another agent to do something differently. And we think this is the second thing that's going to overcome that problem I mentioned of influence not necessarily leading to cooperation. Because our hypothesis is that influential communication should benefit the listener in this case. And that's because the listener is just trying to optimize its own environment reward. It's just trying to pick up apples. So the only reason that it's going to update its policy as a result of a message that's sent is if that message sends it valuable information about how to optimize its own reward. because it's free to ignore the message otherwise. And in fact, its optimal policy would be to ignore the message unless it provides valuable information. So influential communication should benefit the listener. All right, so let's see how well this worked. What we see is by adding the communication channel and then adding the influence reward on top of it, once again, the agents are able to obtain higher collective payoff than the baseline techniques. And we also see that the communication protocols that are learned by the agents tend to indicate that they're more meaningful. So we see that under the influence reward, agents are speaking more consistently about the actions they're actually taking in the environment. And we see this high mutual information between the message and the agent's action when there is influence. But this is maybe the most interesting result. So what you're seeing here is the degree of influence between an influencer agent on the y-axis and an influenced agent on the x-axis. So in the third figure, you see that this agent 0 is very easily influenced by a lot of the other agents. Interestingly, that agent 0 also got higher individual return. But this isn't a coincidence. This is actually an effect we observe very consistently across hundreds of different hyperparameter settings in both environments. So basically, the agents that are more easily influenced or better listeners tend to get higher individual return. And you can think of this as providing support for that hypothesis I mentioned, that influential communication is actually providing valuable information to the listener that's helping it optimize its own rewards. All right, so there are some discussion points I want to go over. So as I mentioned, whether this action-action influence is going to lead to cooperation is going to depend on the environment. So we think that in our environments, the agents learn to gain influence by communicating with each other because they were self-interested. Like they still wanted to be able to optimize their own reward and pick up a lot of apples as well as gain influence. And just sharing information may have been one of the cheapest ways to gain influence without deviating too much from the apple picking policy. Influence on self-interested agents via this cheap talk communication should benefit the listener. It should provide valuable information that the listener can use to optimize its own reward. Otherwise, the listener would ignore it. But this depends on the agents interacting repeatedly. So if I could somehow communicate with an agent that I would never see again, then I could potentially lie and still gain influence. I could say, there's an apple over there, and the agent would move to that location, but there was no apple, I've lied. But if I do that with an agent that I'm going to see again, the other agent is going to learn to ignore my communication messages because I'm not helping it. So there's no way for me to do this in a repeated game. All right, so in conclusion, you can think of social influence as a unified method for promoting both coordination and communication in multi-agent settings. And it enables agents to learn socially, but train independently. So unlike prior work that relies on centralized training, this is a fully decentralized method, so you don't need to have access to other agents' parameters or rewards. All right, so let me pause here in case there are a couple questions before I go on to the next part of the talk. Anyone have a question about this part?
Yes, I have, well, Wolf just raised his hand, so I'll give the word to Wolf.
Oh, Fernando, you can go first, no problem.
I was going to ask if you suggest any type of second-order social dilemma in the sense that if you are influenced and you gain high rewards, and if you give agents the option to be influenced or the influencer, then will everyone want to be in the end the influenced and create another tragedy of the commons?
That's an interesting question. So in these latter two experiments, we do have sort of this like free for all of every agent is trying to influence every other agent. So it's possible for, every agent, there's sort of this like fully connected graph. And so they're sort of they might potentially be competing over the degree of influence that they have. Like sort of if you update more strongly based on one agent's message, maybe you're ignoring another agent's message. But I think that that competitive pressure might actually drive the agents to communicate more clearly, let's say. Yeah. I could take Wolf's question. Yeah.
Yeah, thanks. Just a short question for clarification. Do the agents need to know, or do the agents know that there are other agents in the environment, or could the colors in the grid world also be part of the environment?
That's an interesting question. We build in a couple things that maybe help the agents recognize the other agents as agents, in the sense that we give them an explicit model that is for predicting the actions of other agents, and we feed in the other agent's ground truth actions. So they get a little bit more of a explicit annotation, like this is something you should be paying attention to. And then of course they use their own model to compute that influence reward, which depends on the behavior of the other agents. So again, incentivizing them to care about what the other agents are doing.
Thanks.
Yeah. Sandeep?
Yes, we did some work in the 2007, 2009 on distributed social learning to evolve norms.
Cool.
In those cases, all possible norms had the same utility. Whether they coordinate in a certain way or coordinate in another way didn't matter, really. So, however, in your situation, it might be the case that certain ways of coordinating is better than other ways of coordinating. So, is there a way to, how do you use that? Is that through differential reward structure, or how is that captured?
Yeah, you can think of it as there's some degree of symmetry. Like you can think of all possible communication protocols that I could develop. Like let's say I have 10 symbols and I just want to use one of them to communicate whether there's food. It's sort of exchangeable. Like I could use any of the symbols to communicate that. It doesn't matter. But it might be preferable for me to use one symbol rather than a sequence of symbols, right? So you can just look at like, if I actually want to maximize the mutual information of my communication protocol, that is going to prefer some communication protocols to others. In fact, ones that are more discriminative, right? So it's just purely coming down to what mutual information would say is a better protocol.
And a quick question: in your formulation, you talked about the conditional probability distribution. Does it assume only two bilateral interaction, or is it multilateral interactions can also be modeled? Means who I'm trying to influence might be influenced by other people. Is that taken into consideration?
That's correct. So we have different experiments in the paper. We have some experiments where there's only one agent influencing everyone. The majority of experiments we do, every agent can have influence over every other agent. If that makes sense.
Thank you.
All right, let me move on to the next part of the talk. If you have more questions, maybe we can save to the end of the talk. All right, so I've discussed a little bit about how you can use multi-agent algorithms to solve, a multi-agent problem like coordination. But I'd like to spend the next part of the talk talking about how I think multi-agent training can go beyond this. So it can actually be a useful tool for addressing fundamental issues in AI, like learning and generalization, even if you only care about having a single agent at the end of it. So this is this idea of multi-agent emergent complexity, right? How can we set up a multi-agent system such that because the agents are constantly adapting to each other, they're constantly providing a curriculum of increasingly challenging learning problems that continues to evolve and drives the system to push the agents to learn more complex and interesting behavior. So this is what I'd like to talk about. And I'd like to talk about it in the context of trying to improve generalization and transfer in DeepRL. So obviously we know this is a big issue. If we want to be able to train robots, for example, cheaply in simulation, and then have them deploy to the real world, we want to solve this issue of generalizing effectively. And so a dominant paradigm there is to think about something like domain randomization, which you might be familiar with from the OpenAI robotic hand experiments, where they had a simulator for the hand. And what they did was use domain randomization to randomize the parameters of that simulator and train on many different random samples from that big randomized distribution. And the idea there is that, whatever the real world looks like, I'm going to hope that it looks like some point within this big random distribution that I've trained on so that I can effectively generalize to it. So let's see how well this idea of using domain randomization works in this very simple grid world example. So here we have this blue agent. It's trying to walk towards this green goal, and it's walking around these obstacles. And we're going to use domain randomization to randomize the initial position of the agent and the goal and the obstacles. And we're going to train on many different random samples of environments that look like this. So let's see how well an agent trained with that generalizes to this 4 rooms environment. So what you'll actually see in this video is that this agent is not very effective at walking around walls, which is kind of curious because walls are within the distribution of things that I could have been sampling randomly. And yet the agent hasn't spent enough time training on it that it's actually able to do this behavior. So that's kind of curious, right? What ends up happening in domain randomization is you spend a lot of time training on things that look like the unstructured environment on the left, but you miss specific examples that are salient for humans, like the 4 rooms environment on the right. But let's say, excuse me, let's say you're a roboticist and you really believe in domain randomization. And you say, I'm going to use it to try to train a robot to walk upstairs. So you build a simulator of stairs that has parameters like the width, the height, and the texture of the stairs. And you train in simulation on many different random settings of those parameters. And let's say you actually succeed in obtaining a robot that can effectively walk up this set of stairs in the real world. So you say, fantastic, I'm going to start a company. I'm going to build autonomous household robots. I'm going to make $1 billion. It's going to be amazing. Excuse me. But then, sorry, one sec. But then, oh, sorry. You try to actually deploy that robot to the real world and you notice a problem. Stairs in the real world are very diverse. So it's unlikely that you thought to build this set of diagonal staircases into your simulator. The idea that everything you might encounter in the real world is just going to look like one setting of a few simple parameters, to me, is just untenable. So I think what we need is a series of complex training environments that are going to prepare our agent for these unknown real-world challenges, but we don't want to have to program them ourselves by hand, because this is just going to be brittle. We're going to miss things. We're going to have to spend a lot of time hand engineering. So I don't think this is the right approach. So if we're talking about robustness, maybe we need to think about adversarial robustness. So what if we could actually train a second agent to learn to set the parameters of our simulator in order to challenge our learning agent, our player agent? So what if we take this min-max adversarial formulation and we do just that? So we have this adversary building an environment. What do we think could actually go wrong here, though? Can you see from this video what's going wrong with adversarially generating environments? Exactly. Thank you, Matt. So the environment is impossible to solve. It's impossible to reach the goal. So basically, our adversary, which has been asked to minimize the performance of the agent, has fully succeeded in its goal. It has minimized the agent's performance, but it's created an impossible environment that provides no opportunity for our player agent to learn. So again, we're just wasting computation. This isn't effective. And the problem is that this min-max adversarial game is asymmetric. The environment builder has way more power to make the environment impossible than the agent has to solve the environment. So what prior work has done, where they're using adversarial training in RL, for example, robust adversarial reinforcement learning has an adversary applying forces to agents trying to learn in Muchoco, they've had to hand tune constraints on the adversary that are specific to each new environment. So they say, you know, if you're setting forces in Swimmer, you're not allowed to apply more than X force. If you're in Hopper, don't apply more than Y force. And again, these thresholds have to be hand tuned to each new domain, right? So maybe we could do a little better. And yeah, this is too much hand engineering again. So isn't there a more, sorry guys, just coughing up a storm here. Excuse me. So the idea here is there a more elegant way to ensure the adversary does not create impossible environments? And ideally, we'd actually like those environments to be tailored to the current skill level of our learning agent. So, you know, didn't I just say at the beginning of this that multi-agent environments are good at generating this automatic curriculum that's tailored to the skill level of the agent because the other agents are adapting to it? So maybe the way to solve this problem is actually just to make this a little bit more multi-agent. And so that's the idea behind this algorithm I'm going to talk to you about today. So what we'd like to do is say that instead of having an adversary generated environment for a single player agent, let's constrain that adversary using the performance of a second agent that's going to play the same environment. So we're going to take our player and rename it a protagonist, and we're going to introduce this second agent, the antagonist, that's actually allied with the adversary. And then the adversary's job is going to become to maximize the regret, which is the difference in performance between the antagonist and the protagonist. And so what this does is incentivize the adversary to create environments that are possible to solve because the antagonist is at least getting a high score, but they're still challenging for the protagonist. So they're still targeted towards exploiting the specific weaknesses in the protagonist policy in order to make it more robust. And the reason I'm calling this regret is, as we show in the paper, if you assume that the adversary and the antagonist are a team, they're coordinating, then this becomes a two-player zero-sum game between that team and the protagonist. And if the game reaches a Nash equilibrium, then we can show by the minimax theorem that the protagonist will actually be playing the minimax regret policy, meaning it's minimizing its worst case difference between itself and the optimal policy across all of the environments. And so this is actually a nice objective to make sure that the protagonist is robust. Now, using the idea of using regret, minimax regret, isn't new, of course, but the way we're using it in order to construct environments and do this curriculum learning, we think is kind of interesting. So to give you a little bit more clarity on this paired algorithm, what we're actually doing is we're going to randomly initialize all of the agents. And then until convergence, we're going to have an adversary generate a new environment with a parameter theta. And then we're going to have both the protagonist and antagonist collect several trajectories in that same environment. And the reason we do this is to calculate a more stable estimate of the regret. So what we're going to do is we're actually going to take the maximum of the antagonist trajectories minus the expected value of the protagonist trajectories. So we know that the true regret is the difference between the protagonist and the optimal policy. By taking this maximum, we make the antagonist look a little bit more like the optimal policy. So we end up with a more stable signal of regret. It's more often positive and better at measuring sort of environments that are possible to complete in the best case, but challenging for the protagonist. And then we have the adversary maximize that signal, and both those two agents just maximize their environment rewards. So they're just normal RL agents. And what was interesting about this approach is we were able to show that not only our approach, but all of the approaches I've discussed so far actually connect back to the decision-making under ignorance or decision-making under uncertainty literature. So you can show that domain randomization is equivalent to the principle of insufficient reason. The minimax adversary is equivalent to the maxi-min principle, and paired is equivalent to minimax regret. And the way that we show this is by introducing this new formalism that we call unsupervised environment design. And so basically, instead of thinking about a normal POM-DP, we want to think about a broader class of POM-DPs. So we're talking now about an underspecified POM-DP. So you can think of this UPOM-DP as the space of all possible grid worlds. And then we introduce this set of parameters theta that are used to specify a particular instance of a grid world within that broader class. So theta might specify the positions of all the blocks in the start state in the grid world so that you can then obtain a particular POM-DP within that space of UPOM-DPs. And we can then reason about how to define a policy, which defines a distribution over how to set those parameters theta. And depending on how you define that policy, you recover domain randomization, the minimax adversary, and paired. All right, so that's the new formalism. I do want to highlight why regret is interesting, particularly in the context of generating an automatic curriculum. So I'm going to claim to you that this regret objective is going to incentivize the adversary to create the easiest possible environment that the protagonist cannot yet solve. And this is true under a very simple assumption, which is that the reward for finishing an environment in fewer time steps is going to be higher. And this is true in many RL problems and continuous control problems. If you can do the problem in fewer time steps, it's better. That's true of these environments we're studying as well. And so if that's true, let's actually look at how this works. So here's our regret objective. Let's say the adversary is succeeding in minimizing the performance of the protagonist. So basically that's going to 0 and the second term is disappearing. Then maximizing the regret amounts to maximizing the antagonist reward. And we just said the antagonist reward is going to be higher if it can complete the environment in fewer time steps, which is going to be an environment that's basically has a shorter path to the goals, or an easier environment. So it's very intuitive. Your regret of failing to do an easy environment is going to be higher than your regret of failing to do a harder environment. So this regret objective is leading the adversary to create the easiest possible environment the protagonist cannot yet solve. And that means it's basically incentivizing the adversary to propose tasks in the protagonist's zone of proximal development. So it's tasks that the protagonist doesn't know how to do yet, but it could with just a little bit more training. And that's why it leads to this nice curriculum. And in fact, we do observe that. So here's some plots of the environments that were generated over the course of training. So let's focus on plot C. This is this shortest path length between the start state and the goal state, but it will be 0 if there is no path. So what you can see is that the population-based training minimax, which is our version of POET, if you're familiar with POET, is actually driving this metric towards 0 because it's making increasingly more impossible environments, more often making impossible environments. Paired, in contrast, is continuing to increase this measure. And actually, as you can see in figure D, the agents themselves respond by solving more complex mazes. But what's cool about this is at no point were either the adversary or the agents trained on path length as a metric. This is just something that's emerging out of the training procedure. And we can see in the generated environments, as we suspected, domain randomization is generating these unstructured environments that are not tailored to the skill of the agent. The minimax adversary is generating impossible environments, but paired is like our Goldilocks. It's generating structured, challenging environments. You can see they have corridors in them, but they're still possible for the agent to solve, and they're tailored to the skill level of the agent. So now we wanted to see, will this support our hypothesis that all of this is actually going to improve generalization, which is how we started out. So we're testing here the 0-shot transfer, meaning the agent is just going to be testing these environments, it's not trained on them at all, to a series of challenging environments that were designed by humans. And what we see is that as the complexity of the environment increases, so does the performance gap between paired and the baseline techniques. And for the extremely complex environment, like the maze environment, only paired is showing any hope of solving it at all. And so these results were actually promising enough that we ended up working with a Google product team, working with the Google Assistant team to try to deploy agents based on paired into helping with Google Assistant. So why is this relevant to Google Assistant? Basically, Google would like it if you could say, okay, Google, go book me a flight to Los Angeles leaving on Friday, or okay, Google, go buy me a keyboard. And some AI agent would actually handle navigating that website and putting your information in for you and complete this task for you. Now, this is a very challenging task, not only because navigating websites is a really hard problem, it's very complex, there's many different actions you could take, but generalization is actually a key blocker here, right? Like, let's say you even scraped all of Delta's website and you trained on that and you were able to obtain a website that could, or obtain an agent that could navigate Delta's website and put in your information for you. If you have no generalization, what's going to happen if Delta updates their website? Right? Is your whole system going to go down until you can re-scrape the data and retrain? Like, you need some level of robustness here. So the idea was, could we do something based on paired? And actually, when we were first introduced to the team that was working on this, their initial approach was to hand program a curriculum of easy, medium, and harder websites. And we can see from this graph that on the hardest website, the agent is actually failing to solve the task at all. So basically, we see this as a very hard problem. So our idea was to do something based on paired to actually parameterize an adversary so that it can construct new web navigation tasks out of a series of pages and web elements in order to create a curriculum automatically that would train this agent. And what we see is that a curriculum did emerge. So actually early in training, the adversary chose to build web navigation tasks where there are very few elements per page, but multiple pages. And we think the reason this is easier is because on each page, there's fewer decisions that the agent has to make about what to do on the page before continuing. Late in training, the adversary is constructing websites where all of the elements are dumped onto a single page, making the decision-making task harder. And what's interesting about this is not something we anticipated in terms of how to define easy and hard in this domain, but it's something that emerged over the course of training with this objective. We then tested our agents on a series of web navigation benchmarks. So the existing benchmark, MiniWob, a new harder benchmark that we introduced called GMiniWob, and then a real websites. And what you see is that on the benchmark tasks, our agents are 4 times more successful than the state-of-the-art prior work, reaching more than 95% task success across all difficulty levels on the benchmark. And when we took those agents and deployed them to real websites, we found very promising initial results. We're getting 93% accuracy on the initial easier tasks. So we're very excited to keep working with the Google product team, Google Assistant, and get these deployed. All right, so in conclusion, multi-agent training can be an effective way to improve learning and generalization for a single agent. And we think paired is a good way to think about this because it incentivizes the adversary to build feasible yet challenging environments that are still targeted towards making the protagonist more robust. And this regret objective lends itself nicely to generating this automatic curriculum. All right, so I'm happy to take a couple questions here before I move on to the last part of the talk. So any questions? I saw a comment in the chat that my Google speaker just tried to do a few things based on that last slide. My apologies. And luckily, I don't think those features are built yet. So hopefully you're safe. Any questions about the paired part of the talk before I move on to the last part? Okay, we got a question from Matt.
Very cool stuff. How did you find this opportunity for paired? What made this particular domain good for paired? Because I imagine there are multiple places where you might want to apply it. So what makes a domain better or worse for this?
Great question. So one thing is just that this is something that it's, there's some like coincidence. This is something my manager was interested in and kind of put me onto it. But I think the key reasons why it's important for something like web navigation is that there's a lot of diversity in terms of the web. And so how do you actually focus training time to get the maximum impact on covering that diversity? You need generalization. And it was a really hard problem. And as I mentioned, like the team, before we were introduced to them, were already working on a curriculum-based approach. The curriculum was hand programmed. So it seems obvious to say, hey, let's make this automatic curriculum approach work better. Yeah.
Cool, thank you.
Yeah. Okay, David?
Hey, how do you think paired would scale to, say, multiple antagonists or protagonists kind of working in the same environment as a team? So you have instead of like one agent, you have multiple agents, and I guess as a next step, like you have multiple teams in the same environment that are all kind of working, maybe not together, but working in the same environment.
That's really cool, actually. And it's something I've thought about, but haven't done. What you just need to be able to abstract something about the environment to say, like, what was the success of that team? So you could just think about like the joint reward. And then you could do an approach based on paired where you have sort of like one team is the antagonist and one team is the protagonist. But I think that's quite interesting to think about.
Yeah. Do you think it would kind of, because you might imagine like single agents within that team might learn different behaviors in different scenarios, which might mean that like the team might not get better in the next iteration. So do you think it would, like a different approach would need to be developed or?
Yeah, well, you could think about something a little bit more sophisticated that's more based on population-based training. So actually, I kind of gloss over this in the talk, but for the web navigation work, we do use a population-based approach to paired where we compute the regret as the max of the population minus the mean of the population. So thinking about adapting that kind of population-based approach to like teammates, I have been thinking about that in the context of two-player games where you're trying to cooperate with a partner. And how do you come up with a regret-based objective that makes you robust to the choice of cooperation partner? So hopefully we'll be releasing that work soon, and I can show it to you. I also see in the chat, Matt is saying that you should check out their paper number 36. We have preliminary work on using multiple teachers for automatic curriculum learning, multi-teacher curriculum design for sparse reward environments. So
cool. Thank you, and thank you, Matt.
All right, I'm going to move on to the last part of the talk because I'm quite excited about it and I want to make some time for it. So the last part of the talk is something I'm pretty excited about. It's more recent. This is the idea of trying to do social learning between multiple agents in the same environment where the agents are self-interested. But I'll tell you a bit as I actually get into the slides. So one question you might have asked as I was giving the intro to this talk, I said like social learning lets you stand on the shoulders of giants. Well, so does imitation learning. Right? So what do I mean by social learning and how is it different than just imitating the data of experts? Well, as you might be familiar, imitation learning is just supervised learning on a curated data set of expert trajectories. So you see the states and actions that the expert experienced and you use supervised learning to imitate that or learn that policy. The issue with imitation learning, of course, is that you're copying the data from the experts exactly. You're not being discriminative of which data you're copying. So if your experts are imperfect, then you're always going to perform worse than an agent that can do RL to explore on top of that expert data and refine towards a better policy. So what you're seeing in this figure is a comparison of imitation learning methods against offline RL methods, which are outperforming it in the case of imperfect demonstrations. The other issue with imitation learning is that the resulting policies are brittle and don't generalize effectively. So imitation learning methods are not good at knowing what action to take if they're out of the state action space that they've observed in the data set. And I'll demonstrate that empirically in a few slides. The difference here with social learning, what I'm thinking about here is, how to learn from other agents that are in your environment using RL, basically. And so the idea is that this would work in a more naturalistic setting. If I'm an autonomous car, I'm in a setting where, there are other agents in the environment, but they're not motivated to teach me. They're just going about their own business. They're trying to do their best job at driving on the road. The other agents may also not have relevant expertise. It might be a bad idea to indiscriminately copy every driver because some drivers are bad drivers, right? So you don't want to just copy everyone. Instead of just copying exactly, social learning coming more towards the definition of how it's used in, animal and human social learning, it's a skill about learning how to acquire information from other agents. So learning which models you're supposed to be copying that are effective to copy according to, or like copying which model on which skill, when to use copying versus when to rely on your own individual exploration. And if you learn the skill of learning how to acquire information from other agents, my hypothesis is this can actually help you adapt more effectively to new environments. So we know that this type of social learning helps humans adapt to a new environment. If you go to a new coffee shop and you're not sure where you're supposed to queue to give your order, you can actually figure that out by observing what other people are doing. And so this idea of learning how to acquire information from others can actually help you adapt to new situations because you can figure out how to acquire information from the new experts. And so this is what I'd like to show in the work I'm about to describe. And so the first piece of work is actually done with a student, Kamal. And what we wanted to do was see how much social learning vanilla model-free RL agents do by default. And the way we measured this was to put RL agents in a multi-agent environment where they're with an expert that's constantly demonstrating highly rewarding behavior. So the expert is constantly showing the other agent what to do with its actions. It's just constantly doing the right thing. But what you see is that the agents that are placed into the environment with the experts, shown as this purple line here, perform actually just as poorly as agents that are trained alone from the beginning. And neither of them discover this highly rewarding policy that the experts are demonstrating. So basically, we see no evidence of vanilla model-free RL agents showing social learning. So they're still kind of worse than this little 1-inch fish I talked about at the beginning of the talk. In this paper, we just did a very simple thing to correct this issue. We just added an auxiliary prediction loss. So what we said is the agent has to be able to predict its own next frame in this partially observed environment. But what you'll see is that by predicting its own next frame, it has to also predict the action of the other agent in order to correctly do this. So it's implicitly having to model what the other agent is doing. That appears to be enough to refine its representation sufficiently such that it's now able to benefit from social learning. So now you see this green line is agents with that auxiliary prediction loss placed in the same environment as experts. They eventually reach the same performance as imitation learning, but they were not given direct access to the states and actions of the experts. So they're learning from an agent that happens to be in their environment without any privileged information. So you could think, okay, I'm an autonomous car. I can actually learn from other cars, even if they're not sending me their state and action data. But maybe you say, look, if I were training an autonomous car, I would have a ton of data to access from car. Like if I'm Tesla, I have a bunch of state action pair data. So why is this important? Like why go to all this trouble to reach the same performance as imitation learning? Well, the key difference is this slide. This is about generalization. So once again, here we're testing zero-shot generalization to a series of new tasks that the agents were never trained on. And what you see is that the imitation learners that train on the state action pairs of the expert are shown in this lime green on the right. And you can see that they actually generalize very poorly to the new environment. So showing that they're brittle, as I was claiming before. Even the RL experts that our social learners originally learned from in orange are also generalizing poorly to the new environment, showing RL is brittle as well. But in contrast, these social learners shown in purple are actually performing pretty well across all the environments. Not quite as well as the experts that they're benefiting from, but they're able to essentially use their social learning policy to acquire information from the new experts in the new environment and thus adapt to the new environment. So we think this is pretty interesting. But of course, that was a pretty simple method for doing social learning. We're just doing this auxiliary prediction loss. So can we develop better methods that are specifically engineered to help agents learn from other agents more effectively, do the social learning more effectively? So this method is also with the student Angelos, who's great as well. And what we want to do here is actually use successor features to do social learning. So for those of you not familiar with successor features, I'm going to go into a little bit of detail about what successor features are, and then I'm going to explain how we use them for social learning. So in RL, as you know, we're trying to maximize this total expected future reward. So we sometimes break this down, as I mentioned, in terms of the Q value, which is the total expected reward I expect to get starting in a certain state and taking a certain action. Successor features parameterize that Q value using this interesting division. So it's going to break the Q value down into psi and W. Now, psi is going to do all the hard work of estimating what's happening in the future. Because of course, in RL, you have to learn what's the expected value of everything over time. What psi is doing is it's counting what features of the states I expect to experience over time. So it's accumulating this phi. So let's make this very concrete. Let's say I'm in a grid world and I'm just trying to pick up different types of berries. So I can pick up, or let's say apples and bananas, right? My phi, this internal state feature, might say, did I pick up an apple or a banana at a particular time step? So it's just a bit vector. And then my psi would count how many of each thing I expect to get over the course of an episode if I follow my own policy. So let's say I expect to get 14 apples and 2 bananas, right? The W is just going to be a single vector that's always staying the same. It's not dependent on the state or the action. So it's constant vector. And it's just going to be my preferences over what state features I want to experience in the future. So how much do I like picking up apples versus bananas? And I can combine my preference vector with my psi to compute my Q value. What's the total reward I expect to get? But the reason successor features are interesting is they actually let me generalize really effectively to a new task by just updating my preference vector. So let's say if I've been picking up bananas this whole time, now at test time, I'm asked to do a different task, which is pick up apples. Just by updating my W, I can immediately calculate which action would get me higher rewards if I want to pick up apples according to my psi. And so essentially, for every new task, I don't have to redo all of this very difficult effort of estimating what's going to happen in the future. I can just quickly update my preference vector and generalize function pretty well to new tasks. So this is why successor features are an interesting idea. But how can I use that in the context of multi-agent learning? What we're going to do is we're going to estimate both our own policy, the policy of the ego agent, which is us, as well as the policy of other agents using successor features. So for the ego agent, it's pretty clear I can just learn this Q function with this parameterization using RL as normal. For the other agents, I'm going to be observing their state and action pairs, but not their rewards. But the way that I can estimate their successor features is using maximum entropy inverse RL. So if you're not familiar with that, it's just this model of soft optimality. So we say that the probability that the other agent took an action is exponentially proportional to its Q value. So if the Q value is very high, it's much more likely to take that action, but the other agent can still make mistakes. It's soft optimal, right? So you can think of this as just like a Boltzmann distribution. So I'm going to use this to, by observing the probabilities of other agents' actions empirically, I'm going to use this to estimate their psi and W for every other agent. Now, what am I going to do with that? Well, think about this. I just said the cool thing about successor features is you can quickly calculate the value of a certain policy under a new preference vector. So what I can do is I can say, look, I've modeled all these other agents with successor features. I don't actually care about their preferences. I care about my preferences. So what if I just substitute in my preferences with their psi function? And what that actually allows me to do is say, if I were to act like agent 2, am I going to get higher payoff according to my own preferences? And then I can use this generalized policy improvement to basically take the max over all of the other agents' policies I've observed substituted with my preference vector. So at every single time step, I can say, could I do better right now if I just acted like this other agent? And so the more that I'm able to model the other agents, the more I can kind of steal behaviors from them if I compute that it would pay off for me, which is pretty fun. And the way we actually get this to work, you might have noticed a subtlety here. How do I actually guarantee that, my preference vector W is going to be compatible with another agent psi? Well, how would we choose a phi to actually get this to work? So digging into this a little bit, we can see that the psi is calculating what's going to happen in the future. That's policy specific, right? That depends on the actions that my policy is likely to take or the other agent's policy is likely to take. But this phi, which is the underlying state representation or the feature representation of the state, is actually policy agnostic. So what we do is we say that same phi is going to be shared among all of the other agents that we're modeling. So every agent is going to build their psi out of a shared feature representation phi. And this is cool because now, I'm modeling all these different agents. They're all giving me a lot of signal about what should be in my feature representation of the environment. So if another agent, in order to correctly model another agent, I have to represent something in my feature vector, it's going to help me learn which aspects of the environment are salient to represent. So I'm getting this really nice feature representation. We learn to enforce this with sort of this inverse temporal difference loss. You can think of this as like a Bellman update where we're enforcing that the psis are built out of the phis. And we're also getting this benefit that as an RL agent, our ego agent is actually observing rewards from the environment. And so we know that phi.w should equal the reward that we're observing if we use our own ego preferences. So this gives us even more signal that helps us refine that shared feature representation phi. So I know this was a lot of math, but just zooming out a little bit, basically what you're getting is that when you learn to model others more effectively, then you can actually learn to act more effectively by borrowing from their policy. And as you interact with the environment more yourself, that's going to refine your phi, which is going to improve your modeling of other agents. So you get this feedback loop where the more you learn from others, the better you act. The more you act, the more you can effectively model others. So I'm just going to quickly go over the results. I hope we're not too out of time. Please let me know if we are. We tested this in a variety of experiments. What we see is pretty fun. If the other agents are doing exactly what you need to do, the best thing you can do is just imitate them exactly. And we see that the imitation learning methods perform best in that case, and our method is pretty competitive. If the other agents are doing exactly the wrong thing, so they're all just parking on the highway, then you can see that imitating them is catastrophically bad, but our method performs competitively with the RL methods. But when the other agents in this more realistic setting, where some of the other agents are doing relevant things and some of them are doing irrelevant things, you see that imitation learning doesn't perform well, but our method actually outperforms the other methods in this multitask setting. So we think of that as effective. We also get some side benefits that we're more able to model other agents more effectively. So we predict their next action. We also are able to model their rewards, what reward function they're optimizing with inverse RL. And we actually do better few-shot generalization. So, even if you've never ever picked up a banana during training time, if you've observed some other agent picking up bananas, you've effectively modeled that. You can adapt one shot to doing that new task at test time just by updating your preference vector, whereas imitation learning would take 100 shots to adapt. So we're doing a little better now. We're getting a little closer to this 1-inch fish. So in conclusion, social learning is a powerful mechanism that can help RL agents rapidly adapt to new environments and learn complex behavior. And I realize I am out of time, so I'll just stop there in case there are questions.
Thanks a lot, Natasha, for a fantastic talk. And I think, yeah, it's fine. We're actually scheduled until we have 12 minutes for questions.
Okay, good.
So any questions? I think there was a question by Herman before. I'm not sure if you still have it, Herman.
Hi. Hello. Yeah, my question was, maybe it was about the first part of the talk. Maybe I missed that. How do you measure the cooperation?
Right. So we basically measure the collective return of all of the agents in these social dilemma environments. And that's suggestive of cooperation because you can't obtain high collective return unless you're actually solving sort of the tragedy of the commons problem.
Okay, so we don't necessarily know if the agent intends to do it, but at some point it acts in a way that solves it, and that's what we are counting. Right?
Mm-hmm. Yeah.
Thanks.
We also measure the equality of, or the Gini index of agent scores to see if they're harvesting more equitably. That's in the paper as well.
Right.
Any other questions? Oh, David?
Hey, so I might be misremembering from that paper that we were just talking about, but why does the influencing agent not go and get the apple? Do they only get reward from influencing other agents?
They also get a reward for collecting apples themselves. So they will get an apple if they can see one, but they sacrifice exploring, basically. So when there's no apples, they stay still, but if there is an apple, they walk towards it.
So
and
them moving to go get the apple for themselves kind of signals to the other agents that there's an apple over there.
Exactly.
Okay, so are there any cases where the agent that they're signaling to beats them to it? Because technically, like, they wouldn't be able to see the apple before the influencer agent sees it.
I don't have stats on that. It's quite possible, but I don't have a way of calculating that.
Okay, thanks.
Bram?
Hi, thank you very much for the interesting talk. I was wondering, maybe I missed it if you already mentioned it, but how quickly are you able to adapt to the behavior of another agents that you see would be really beneficial for yourself? Because you can't really take their parameters, right? Or how do you do that?
Right. Yeah, I kind of rushed through this part because I thought I was running out of time, but just to go back to that, at every time step, you can take your sort of state-of-the-art model of the other agent and use it to choose an action. So essentially, like, I'm modeling, let's say, agent 1, I have its psi 1, I replace it with my preference vector. If I compute that following that other agent's suggested action under my preference vector would pay off better than following my own policy, I can just use their policy.
Okay.
Yeah.
Okay. So you keep track of an own copy of their model that you're trying to keep track of how they're.
And that's actually a subtlety. So because I don't have access to their ground truth model, this is actually my estimation of them. It's my model of them, but it isn't what they're actually using to act.
Right.
Yeah. Okay.
Nice. Yeah. Thanks.
No problem. Other questions?
If there are no more questions, we also created a channel in our Slack for people to discuss. You're welcome to join, or can also forward you any questions or comments that we find there.
That sounds good.
And if there are no more questions, yeah, a lot of nice messages in the chat as you can read.
Well, thank you so much, guys. I really appreciate being here.
Yeah, thanks a lot for accepting our invitation. There's actually a poster session now, a joint poster session on Gather Town with 2 other workshops for the next hour. So anyone that feels like joining, please do it. And we'll come back tomorrow for our invited talks with Erke and Bai. So thanks again thanks a lot, Natasha, once again, and thanks everyone for joining. And see you tomorrow. I can hear some claps.